All right, so the goal of this video is to show how to find area between two curves. And honestly, it's really just based on finding area under the curve up until the x-axis. And so, that's why this first question says, find the area shaded. So from 0 to 6 of this area under the parabola. So we can set up an integral and do this relatively, hopefully simply. And so our integral will be from 0 up to 6 of negative x squared plus 8x dx, which would be negative x cubed over 3 plus 8x squared over 2, so 4x squared, when evaluated from 0 to 6. So we put in our values of 6 and 0, so negative 6 cubed over 3 plus 4 times 6 squared, which is 36, minus when we put in 0, which is always nice. And so then negative 6 cubed is 216. So negative 216 over 3 plus 4 times 36, which is 24. Carry my 2, 144. This is negative 72 plus 144. So we get an area of 72. Now, what I'm going to do is now find the area of this curve. And, again, we can use calculus if you want. Actually, we should, right? So even though we wouldn't have to, but it's the area from 0 to 6 of 2x dx, which means it's x squared. That's weird. Try that again. X squared from 0 to 6. So that's equal to 36 minus 0, which is 36. And what I want us to see that is you can think about the area in our first curve, which would have continued all the way down here, right? If you think about like that region, that's the region we started with initially. And then what we just did was the triangular region down here. So if we were to remove the triangular region from the red region, we'd have a region that's bound between two curves. One of them, or actually neither of them, are the x-axis. And then that's exactly my point, is that you can find the area between two curves if you have a boundary, like a top boundary and a bottom boundary, and you just simply set up your integral based on, well, what's the top height going to be? And then the bottom height, it's like you're taking away that much. And so that's going to leave you with just the amount that's in between the two. And so if you wanted to set that up, you could say it's from 0 to 6 of, I would say, like it's the top curve minus the bottom curve, just to kind of start us out here. And it's in terms of x dx. So then our top curve would be the quadratic. So we could say, oh, that's from 0 to 6 of the top curve, negative x squared plus 8x, minus the bottom curve, 2x. And once you have it set up geometrically, then you can just like start simplifying it algebraically, right? Like there's no reason why I have to to do these integrals separately. Just combine any kind of like terms that you could. So negative x squared, 8 minus 2 would be plus 6x dx. And then when you integrate this, so here's our negative x cubed over 3. This would be 6x squared over 2, or 3x squared, when evaluated from 0 to 6, and then you put in your 6, so negative 6 cubed over 3 plus 3 times 6 squared, and then minus 0, which is really nice. And then, we knew that, go back. So we knew that 6 cubed was 216, and then 216 over 3 was negative 72 plus, and then 6 squared is 36, times 3 is 108, and added them up equals 36, which is exactly what we should have gotten, because we found that the red region in problem 1, the whole thing was 72. You took away 36, and so we get 36. Now, it's just a coincidence, right? Just a coincidence that it was exactly half. Like I just picked numbers to work out relatively nicely. But here's the thing now we have to remember. when we remove the x-axis, this is probably so important. When we remove the x-axis, you no longer are comparing it as displacement. In other words, there is no longer negative area. When you are bound between two curves, it is always going to be positive. So I'm looking at this right here, and I see, a majority of this is going to be under the x-axis. It doesn't matter because no longer are we comparing it to the x-axis. So there's no displacement. It's always going to be positive when we're talking about area bound between two curves, just as a heads up on that. Okay. So, in this case, I want to find the area between these two curves. Region looks very similar to what we just found, where almost like a thumbnail, right? Where you have a top part's parabola and the bottom part's linear. And again, it doesn't matter that part of this is below the x-axis, as long as everywhere the curve is like top minus bottom, is bound between two separate functions, because we got to go all the way back to this idea of finding infinite number of rectangles, right? And so as long as we can measure top minus bottom to find, that's always bound between those two curves, the integral is going to allow us to add up those infinite number of rectangles that are, infinitely thin. It basically are just lines and not rectangles at all. So, but we do have to identify the top function, which is easy in this case because it's the quadratic one, and then the bottom function, which is linear. Now, it doesn't tell us where to set the bounds, but we could see the left bound would be 1, 2, 3, 4, 5. So it looks like that's -5. The right bound would be 0. So I'm going to grade from left to right, so -5 to 0 of top function, -x² minus 4x minus 2 minus the bottom function, x minus 2. And you really want to make sure you keep track of your parentheses here, because each function, right, is going to be treated as a unit, right, as an entity. Okay, so let's simplify some things before we do the integral. So -5 to 0, there's only one quadratic. We do get -4x minus x, so it's -5x. And then we get -2 minus a -2, which becomes +2. So those will cancel out. So here's the quadratic. So that's -x³ over 3 minus 5x² over 2. And we're going to evaluate that from -5 to 0. Well, here's nice. The 0 came first, right? So we get 0 minus, and then again, I would definitely use parentheses. So we put -5 in there. -5 cubed is -125, but there's that extra negative there. So it becomes +125 over 3 minus, and then -5 squared is 25 positive, and then 25 times 5 is 125 over 2. And so when we could distribute this negative if we want. So you get -125 over 3 plus 125 over 2, which is good because we want it to be a positive value, right? Because we know that it doesn't matter where it exists below the x-axis. It does not matter. It gets still a positive value. Let's find a common denominator, which would be 6. So then we double that. So it'll be like -250 over 6. Plus, and we triple that, so 375 over 6. So we end up getting 125 over 6. Excellent. Okay, so again, identifying top function, identifying bottom function. And now here, I like this example too, and we'll set this up because it just says write but do not solve. And that is part of what I want to talk about in this video too on the AP exam, because they're going to have questions where they're going to test you on how to do antiderivatives and how to do fundamental theorems of calculus, right? The fundamental theorem of calculus. But now they also want to test you on application, but they don't necessarily have to have you solve it through to completion. If you can just set it up, they're testing, oh yeah, you applied, an integral to this particular situation. My point that I want to show here is that they give us a curve so they can at least see, we could see the region R, right? We could see the top function is the linear function and the bottom function is the quadratic. So if I'm going to set this integral up, I would say the top function, which is the quantity 2x plus 6, minus the bottom function, which is half x squared. So forget your dx. But what they're not showing and they're not telling us, and we don't see directly, are our bounds. So yeah, we still need to find those. So then we just do a little bit of algebra. So sometimes you like you may have to find those bounds. And honestly, sometimes they might not even give you the graph. So you have to have a little bit of a sketch, an idea of which one's on top, which one's on bottom. Kind of draw it out off to the side. So let's solve for those bounds. So I don't remember what color I picked. Let's go blue just for fun. So 1/2 x squared. When does that equal 2x plus 6? Well, we could double both sides to get rid of the fraction. So that's 4x plus 12. Subtract x squared minus 4x minus 12 equals 0. We want two values because we know it intersects twice. So it looks like it's at -2 and at 6. And so this makes sense. There's the -2. There's the 6. So then I would say, okay, there it is. And like I said, like a lot of times in this particular section, it's a lot of application, especially geometric application. You might just have to set up an integral and that's it. You don't necessarily have to solve it through. I mean, this bothers me just a bit. Let's fix that 6. That looks really super ugly. Sorry about that. So now I can fix that. 2x plus 6 as a quantity minus 1/2 x squared. Excellent. So, hopefully that gives you a good idea to start with some of these examples, and then we'll just, continue to work through the rest of the examples on this page.